You good? Okay. Okay. Today I want to talk about systems. When I was doing some research on the internet over systems, if you Google the word system, there's a lot of different contexts for system. For example, a system could be like a system of the body, like say the cardiovascular system. That makes sense. System could be like a water filtration system. And so when I was looking for how to define system, I felt like I needed to make sure it was in the context of what we're doing for physics. So I actually went to your textbook and looked up what it said for system there. And so here's the definition. Two or more objects that interact with each other. Okay, well that's very bland definition. Can we narrow it down more? So I put it in my own words. I decided to make my own kind of definition. So here, I'm just going to read off my slide. Essentially, a system is the portion of the universe you want to look at. For example, a system could be our classroom. If we want to study how things work in our classroom, that's a system. Or maybe the system could be the entire planet itself. When we were working on like universal gravitation stuff, and we're talking about how like a planet orbits the actual sun, maybe the system is the planet, the entire thing. In biology, maybe the system you're talking about is the cell. That makes sense? So, of everything in the entire universe, sometimes we have to simplify and just talk about just like a certain little section of it. So that's a system. Everything outside of the designated boundaries is ignored. Does that make sense? So, portion it off so that you're talking about something specific. Okay. There are three main types of systems, and have you guys ever heard these terms before? If you have, that's great. If not, let me just redefine them for you. There's a closed, open, and isolated system. An open system is the kind of system where you can have matter and energy go in and out of. Okay. A closed system, matter is not allowed in and out. And an isolated system, in theory, nothing should go in or out, neither matter nor energy. Isolated systems are, for the most part, like theoretically impossible. You really can't get a true isolated system. But we're going to try to assume that systems are isolated anyways. So I got a bunch of pictures just to illustrate examples here. So just in case you missed those definitions, an open system, you can have mass and energy both go in willingly, back and forth. A closed system means that, like, you put the lid on the jar. Now matter should not be able to go back and forth, but maybe energy can still move. And then isolated is neither. So here's an example I found. Imagine you have a jar of water outside. In an open system, you don't put a lid on it. And so if someone accidentally hits a baseball and it splashes into your jar, is that going to screw up your experiment? You say, yeah, that's probably not a good thing. Right, so that's an open system where stuff could come inside. Okay. And ideally, you don't want to have that. Right? You want to keep it so that matter is not able to enter or exit. A closed system means that you might put, like, say, a lid on top of it. Now, can the baseball get inside? I'd say, well, no. That's good news. But energy can still get inside. So for example, if the sun is beating down on this thing, your system could be changed because the temperature could increase. Does that make sense? And so that means energy could either enter or leave or something like that. An isolated system would be then like if you tried to like, well, you guys know the word isolate, like insulation maybe would be a good example. If you insulated it like a thermos, well now hopefully if the sun tries to beat on this here, it actually reflects away and the temperature stays the same. That being said, even like a thermos, will a thermos eventually either lose or gain heat over time? Yeah, slowly it will. Maybe you've heard of the first law of thermodynamics. Basically it means that heat will be transferred from like, well actually it's the second law, but that energy will be conserved, but it will need to transfer from some form to another. So you are going to lose heat. Same example here, just with different visuals. Here's the open system, the beaker with the lid off of it. If you were doing a chemistry experiment and you left the lid off for large periods of time, I would say that's a poor experiment because you could get contamination inside your beaker. So, better way of doing it, put the stopper on top of the flask. Now it's a closed system. Isolated system, put it in a thermos. Well, nearly isolated system though. Make sense? Right. One last slide, then I'm done. Okay. Next week we're going to talk a lot about how energy can convert from different forms. For example, you can convert energy from chemical energy to kinetic energy. A battery does that. Like imagine the battery in that clock right there. Kinetic energy, because the hand on the clock is now moving, there's actually motion to it. Why is it moving though? It's not moving due to gravity. It's moving because the battery is converting chemical energy into energy that causes motion. That makes sense. Kinetic energy then could happen to convert to thermal energy. If I were to take Kinsey Ann and put her down a slide, she has kinetic energy as she's going down the slide because she's speeding up. Why would there be thermal energy as she goes down the slide? Yeah, friction, right? And so she might actually feel a little bit of like a burn. You know, like you ever get a rug burn or something like that when you slide against something? That's that friction, that thermal energy. Okay, last terms I want you guys to know here, and hopefully you've heard these at some point in your life, but if not, it's not the end of the world. The first law of thermodynamics is sometimes known as the law of conservation of energy. Long story short, physicists believe that there is a finite amount of energy in the universe. There is only so much. You cannot create energy, you cannot destroy energy, but you can convert it between forms. So I could convert my potential energy into kinetic energy. I could do some work and lift that back up to give me more potential energy. I can convert between forms of energy, but I can't actually destroy it. Does that make sense? And so that's the first law of thermodynamics. Our goal next week is going to be to solve questions keeping track of energies. In our second unit on dynamics, our goal was to keep track of different forces. Well, we're going to do almost the exact same thing, but we're just going to make different energy values equal to each other. Does that make sense? Our assumption is going to be that things happen in isolated systems, where ideally there should be no heat loss due to friction, but that's probably not true. Let me just show you my simulator one last time here of this guy going back and forth. Just bring him back up to the top here. Play. There's actually 3 types of energy listed here on this bar graph here. There's this kinetic energy, there's this potential energy.
Rojan Moore, please come to the office. Rojan, to the office, please.
And apparently there's also a little bit of thermal energy. Watch what happens when I go and I turn the track friction up a little bit more. Eventually he's going to slow down and not go quite as high anymore. Because of what? Yeah. Friction is now making it so that he's losing all of his energy, and all of his energy has now been converted into thermal energy. And now his skateboard / his wheels / the actual ramp itself is now slightly warmer. Has that energy been lost? No, it's just merely been converted. It's now that energy is now stored inside the actual slide or inside the actual skateboard, and the temperature has probably gone up maybe like half a degree. Let me just show that one more time here. So kinetic to potential back and forth, but slowly we'll slow down. You guys ever heard of a perpetual motion machine? Ever heard that term before? Perpetual motion machine? The idea behind this would be that you'd create a machine that once you start it, it would never stop. It would just keep going and keep going and keep going. And in theory, those should never exist because you should have slight amounts of energy converted, probably, it's usually friction, is the thing that causes them to slow down. That makes sense. And so if you've ever heard that term perpetual motion machine, in theory they're actually impossible because even if I had this coefficient of friction down like the smallest amount, it's about as low as I can get it, I guess, he should eventually slow down. Do you guys know what a Newton's cradle is? It's one of those devices that you might see like as a paperweight on a desk. It's usually 5 balls next to each other, and then you pull one of them back, and then it like clicks, and then the far one comes out and it comes back and it clicks and it goes back and forth and back and forth. You ever seen one of those? That's another good example of how you're going to have potential energy turn into kinetic energy. That kinetic energy kicks the far ball out, turns into potential energy, and back and forth and back and forth. But that Newton's cradle will eventually stop. Energy wasn't lost, though. It was just converted into some sort of form of heat, probably. Well, actually, there's one more form of energy that's getting lost there, too. Sound. Because every time it makes a click, the sound energy is also slightly lost. Makes sense?
What happens when it cools down?
What was that?
It's like heats up from the energy or from friction.
Okay.
And then it cools down.
Well, that just means that energy then went to somewhere else. right? So like I don't know, like imagine that heat then was like a candle, right? That heat isn't lost; it's just heating up the rest of the world slowly but surely. It won't heat it up a whole lot, like maybe like a tenth of a degree, but you know, slowly but surely the heat then from the actual skateboard will heat up the air around it. So it's not lost; it's just converted. Any questions? Just you swatting a fly?
Yeah.
You guys have any questions? Okay, that's all I got, guys. Can I ask for two things then before you leave today? Make sure your lab is done. Make sure your assignment is done. If you finish those things, relax.